Hi everyone. Hope you guys had a great weekend. The fellowship is ramping up. We posted a bounty, as you guys saw in the Discord. Hopefully, it will push you to turbocharge your digging into Summa. Also, we are starting the series of code-based overview, starting with today. So the rubber hit the road last week, but now we hear scratching sounds. And all right, without further ado, welcome Enrico, and the mic is yours.
Okay, thanks, Oba. So we'll start screen sharing. So like today, as Oba mentioned, we're gonna go through Summa. So we're gonna go start like speaking into the protocol. Like we're not gonna touch the code base yet, but let's say we're gonna kind of go tangent to the code base. That will be on Wednesday will be Elo 2 by nullity, and on Friday we're gonna start like the code base overview. So I'm gonna, well, okay. So first of all, like what's Summa? As you know, it's a proof of solvency solution, and it's been developed within PSC and the Ethereum Foundation. So I think I never mentioned it before. Maybe you know already, but this makes it as a public good. So as you know, everything is open source, and it's not that we are like kind of building a business out of it. But if someone, even if some of you wants to make a business out of Summa, it's completely fine, and we'll help you doing that. This is like a tangent. Anyway, what are like the focuses of Summa? First of all, we focus on privacy. So as we already discussed, there are like different type of ways of implementing proof of solvency, and we maximize the privacy for like the sensitive data of the custodian and its user using zk, and we don't yet cover the privacy in terms of the assets. So we don't hide the addresses and the balances of the custodian. There are like solution on that, like what Ali is working on, but there are like some issue there. So we didn't want to go fully into that because we think it's not fully secure yet. We focus on performance. So as we see already, we want to make possible to run rounds of proof of solvency with high frequency at a low cost. So for that, we have a blog post that is gonna be released very soon, but you can already see the benchmarks on our Gitbook. So in general, if you are like targeting a user base of 2 to the 28 user, you should be able to run a whole round in around an hour, and it should cost you around like, I don't remember, but I think it was like $15 or, well, like this order of magnitude. So I think this is a good result. And also we focus on UX. So we're gonna see this later today on how you can perform the verification. But if you have tried one of the existing solution for existing exchanges, you will notice that the verification in terms of the proof of inclusion verification is it's kind of bad because, you know, it must be transparent. So it cannot be like kind of just like a button on a browser that says like verify the proof, because you don't really know what's happening if you do it like that. But what current exchanges are doing is that they make you like clone a repository and like run the code locally. So this is good for transparency, of course, but for an average user is not it's not good. So what we are trying to achieve is like both transparency for like people should see the code that is running under the hood, and on the same time like a kind of a good enough UX. So I'm gonna go through the proof of solvency, well, Summa round flow, and I think this is the best way to understand what's Summa. I'm gonna go through that rather quickly, then take question if you have, and then we're gonna go more into the proving side, and I want to focus more on that. So that's why I will go let's say, rather quickly on that, because this is basically what you can also see on the Gitbook. So first of all, there's the, so let's see the overview first. The custodian is first generating this address ownership proof. So this is a proof that they control some address. Then they send the liabilities commitment. So in Summa, the liabilities are built out of a Merkle-sum tree. So the liabilities commitment is the root of this Merkle-sum tree, and the root is composed by both the root hash and the root balance. And then the last part is the inclusion proof. So the custodian will generate an inclusion proof for each individual user. So this is different for each user. And starting from the inclusion proof, starting from the liabilities commitment, the user can tell if they've been included correctly in the liabilities commitment. And the solvency, let's say the solvency is like assessed at this step, like after the liabilities commitment. So the liabilities commitment tells you the total amount of liabilities of the custodian. And then this liabilities commitment also comes with a timestamp. So starting from the timestamp, you can also fetch the assets owned by these addresses at that timestamp. So you can kind of compare it yourself. So you can say, okay, these are the liabilities, these are the assets. Are the assets greater than the liabilities? So let's start with the first, the address ownership proof. So this is rather simple. Like I kind of made reference to that in the first session, that we don't focus too much on this part while we focus more on the liabilities, also in terms of the code base we developed. And this is very simple. Like we ask the custodian to group their wallet, sign a message, and submit this message on chain. So what we really do, and you will see this in the backend, is like we accept a CSV file as an input, and we simply transform that into something that can be consumed and parsed by Solidity. So this is like everything that we touch on the assets of the custodian. And this is also like a, I would say, a smart choice, because you know, every custodian has like very strict and weird and customized policy for managing their own keys. So we don't want to deal with that. We just let them sign however they want and give us this CSV file. So in this case, you see, you need to specify the chain that the address is belongs to, and then you take a message that in this case is like Summa proof of solvency for crypto exchange, but you will see that we don't constrain them to use a specific message. And this bunch of signatures are stored optimistically on chain. And when I say optimistically, I mean that we don't perform the verification on the signature. And I made also reference to that before, but this is because we want to support every chain. So since the contract is developed on, is deployed on a EVM compatible chain, we will need to add support for every signature type. And it would be like complex from an engineering perspective, but I would say still doable. But it will add cost because it will require more gas to verify this proof. And it doesn't really add any security to the system, because since these signatures are out there, they can be verified and they are like going to be there forever. So I think like we don't really need to trigger any on-chain action based on this signature verification or not. So that's why we excluded the verification part on-chain. And there are like tons of software that allows you to verify this proof, I don't know, written in JavaScript or Rust. So we don't have to worry about that. This is not included in Summa. And also this address ownership proof part doesn't need to be performed for each round. So if you think a custodian that only has like 5 addresses and it will be like them forever, then this can be done only once, and then we can kind of keep using this address ownership proof forever. While it's different if they add a new wallet to their set of wallets, then you need to update this address ownership proof. I mean, not update, like, yeah, just add this new wallet. The other ones, we kind of assume that are maintained and are still owned by the custodian. And how does this verification happen? As I said before, this can be done by anyone, and it's simply like a signature verification. So you take the address, the message, the signature, and it returns true or false. And some other things that you might need to want to check is that if the message is kind of relevant to the proof of solvency round. Because if I claim that I'm controlling an address, but the message signed is like, I don't know, like something that is completely outside of the scope of a proof of solvency, like a transaction or, I don't know, an authentication message, then you can be kind of suspicious that maybe they don't actually control this wallet, but they just took a signature from the wild and they're claiming it to be theirs. But this is more like a subjective opinion. It's not really, we cannot really enforce this, honestly. And also, we discussed it last time. Since these addresses and these wallets are public, then everyone can also check their behavior. So if they see that at every proof of solvency round, they're like suddenly a lot of token and currency flowing into these addresses, then you should be suspicious. If like let's say the stake of these addresses is kind of constant, or is like kind of gradually growing or through time, then it's kind of seems more legit. But the important thing is that these addresses are public, are known by everyone. So everyone can make their own opinion and judge if they can trust the custodian or not. Then there's the liabilities commitment part. So you build a Merkle-sum, you as a custodian, the custodian builds a Merkle-sum tree based on a snapshot of the user-based state. So I said before, for the signatures, we were relying on a CSV file. You see that there's the case also for the Merkle-sum tree. So I wanted to show you this. Like you will see like in the backend, the way the custodian interacts with Summa, and the way they kind of kickstart the building of a Merkle-sum tree. They provide a CSV file with the username and the balances. So again, we don't touch the database or like the backend of the custodian. We just ask them to give us to build this CSV file by themselves, and then when they have it, we use that. I mean, they kind of locally run this function to build the Merkle-sum tree, and once they have this Merkle-sum tree built, they submit the root hash and the root balance on chain, so to the smart contract, together with a timestamp. So the timestamp is like a Unix timestamp of when the snapshot was taken. And how this, so as I said before, now we can perform the verification of the solvency of the custodian. Again, this can be done by anyone, and how you can do that. So assuming that you verified the signature as mentioned in the previous step, you fetch the addresses that were committed in the previous step, and then you fetch the assets controlled by these addresses at the timestamp. So we are like now, let's say we are operating in a setting when there's like only one currency. So like the proof of solvency is built only for it as a currency. So you can fetch the address, the Ethereum addresses of the custodian. Then starting from the timestamp, you can go to a block explorer and query the balance of these addresses at the next available block at the timestamp. So this is important, like the snapshot of the liabilities should be as much synchronous as possible to the snapshot of the assets. So you cannot fetch the asset state right now and compare it with the liabilities commitment that was snapshotted yesterday. So we know that like the timestamp, you cannot, it's not that like for every second, Unix second, there's a corresponding block cache. Like there's like some difference, probably like some seconds, or maybe for Bitcoin even a minute or a few minutes. But we should try to get as much synchronicity as possible between these two states. And maybe this is also probably an interesting challenge if you think that there might be some attack that can be done leveraging the fact that, you know, you cannot have a block hash every second, every real world second. So maybe there's a way to trick the system using this let's say design property of like how blockchain works. So this is also an interesting challenge. But once you have done that, you sum the assets together and you simply compare this asset sum with the liability sum, which is the root balance of the Merkle tree, which was committed here. So, like as we already mentioned before in the previous session, like the fact that now the custodian is solvent doesn't mean that they are actually solvent, because when they committed this, when they performed this liabilities commitment, they could just say whatever they want. Honestly, like there's no check performed here, so they could have just said like, yeah, my liabilities committed are like 1 ETH. Don't worry, I have like 2 ETH, so now I'm solvent. But the core part, as we said like many times, comes with the inclusion proof. So yes, we don't, there's no guarantee yet that the Merkle tree was built in a legitimate way, a legit way. And the inclusion proof is generating for each user who requests it. And this inclusion proof will prove that they have been accounted for correctly in the liabilities. So technically inside this Merkle tree. And notice that here I specify for each user who requests it, because given the time it takes us to generate a proof of inclusion, we cannot pre-generate it for, I mean, if the user base is like very small, then probably we can. But every time we consider a benchmark, we use 2 to the 28 user, which is the user base of Binance. And in that case, generating a 150 million proof will be, I mean, we can parallelize it as much as possible, but it will be expensive. So we don't do that. We only generate a proof on demand. So how does the verification of this inclusion proof work? And notice that I didn't mention it, but like this inclusion proof is the only ZK proof in the system. So now we are talking about a zero knowledge proof. So compared to the other proofs, this can only be verified by the user, only by the user who it was generated for, because we work under the assumption that the user is the only one who knows their balance correctly. So if I give Ali the proof of inclusion of Enrico, it doesn't know what was my balance at the timestamp. So yeah, it can verify the cryptographic proof, but it cannot perform a verification checking if the public inputs were correct. So I'm gonna go through that also later more in depth. If you didn't understand it yet, it's fine. But this is how you as a user receiving the proof, you can assess the validity of the proof. So first of all, you take the proof and you verify that. So this is simply like, let's say, the verify API of any zero knowledge proof system. So now we are sure that the cryptographic proof is valid. But then we need to make some further check on the public inputs of the proof. So this is true not only for Summa, but like also for most of the proofs. Like you can get, maybe you're more familiar with like semaphore. This is like a simple Merkle tree inclusion. Like I can get a valid proof of inclusion that verifies this step 1, but maybe this was like a proof of inclusion based on a different tree. So this was proving my inclusion inside a different tree, not the one that it was supposed to. So you will detect that this proof is not valid when you see like the public input that is like the root hash. So that's the same for Summa. We need to check that the root commitment, which is the public input of the proof, is matching the one that was published in the previous step associated with this timestamp. So the root commitment is made of the root hash and the root balance. These are public input of the proofs. And when you receive the proof, you basically need to check if these are matching the one committed to in the previous step. And also the other public input of the proof is the leaf hash, which, if you remember from the diagram of the Merkle tree, is equal to hash Alice 10, for example, where Alice is the username of the user and 10 is their balance in ETH. So they need to take this leaf hash, they need to perform the hashing based on their username and their balance at the timestamp and see if this is matching. Because if this is not matching, there's something wrong. It means that they use a wrong balance, or this is not their username. So that's how you check the validity of the inclusion proof. And yeah, last thing is that the way we allow user to perform this verification is through a view function on the smart contract. So a view function on the smart contract is like a gasless function that doesn't update the state of the blockchain. So it's really like a simple API that allows you to interact with the smart contract, so you can see what is like the code being performed, but this doesn't update the state. So you don't have to have a wallet to do that. You don't have to pay gas. So this is also, I would say, kind of rather user-friendly. And the way you can do that, for example, is like through Etherscan. When you verify a contract, then there's like this way, this interface. So you can, when you receive the proof of inclusion, you can copy and paste it here and run this function, and it will return true or false. And on top of that, you will need to perform. So like this verification, this cryptographic proof verification is performed in this function. The fact that the root commitment is matching the one committed by the custodian in the previous step is also verified in this function. While we cannot verify in this function is the last thing, that the leaf hash is matching the user data. So the user must need to do this hashing outside of this function. And just for the record, we are using Poseidon hashing, so because it's kind of efficient in the ZK circuit. I will say a few things more and then take the question if there are. So there are like some other verification that are a bit more subtle and probably not for every user. Like it's kind of already difficult to explain everything up to this point, but I think this is even more difficult to explain. So we need to perform some verification on the smart contract, right? Because when you have like a verification, like a verifier smart contract developed on chain, deployed on chain, you need to check if this is legit. So I can have my circuit, my all logic written in GitHub, and it's open source and everyone can see that. But if then I deploy a verifier that is based on a completely different circuit, then everything is like kind of pointless. I mean, it's kind of a way to influence the protocol maliciously. So it's like an attack, basically. And well, what someone need to do to check that if was done properly is to run a function that we also provide that allows you to regenerate this verifier contract. And this verifier contract generation function takes as an input the declare, the circuit. So in this case, the proof of inclusion, Merkle-Sum tree proof of inclusion circuit, and the trusted setup that also the custodian should declare to the public, and one should check if the output is correct. And I want to say that this is basically for every ZK project. So even like a ZK EVM, when you see their code base that is public, this is okay, but everything, the core logic relies on the verifier they deploy on chain, and everyone, I mean, I think this should be like kind of off topic. Like this should be like a tooling that is provided by the community, and something like Etherscan that is able to verify that some contract code is matching like the corresponding circuit code. So yeah, that's also another check that needs to be performed anyway by the public. So this can be done by anyone. And also the last check is that we need to check that there's no chance of overflow. So as we said before, the logic of our circuit is based on a Merkle-Sum tree that has some levels, and we range check that the balances are inside of a byte range. But if we set like a very, very high byte range, and the levels is also very high, probably there's like some chance that this summation actually results in an overflow. And I want to show you this thing. So if you go inside ZK Prover, well, we're gonna go through that again, but just to show you now, there's like this this script to generate the inclusion verifier. That this is something that we use also internally to generate the verifier function, but this can be done. This can be used also by people outside to check if the verifier contract is matching the circuit. And if you see here, there's also this assertion that check if there's a risk overflow given a particular combination of bytes and levels. Okay, so I will take questions now. Last thing is that we develop the whole logic based on the smart contract interaction, but it's not compulsory to use the smart contract. You can also do the whole liabilities commitment, and basically you can publish this stuff rather than on Ethereum. You can publish them on your server, and we don't encourage doing that because of course you're gonna lose this kind of property that when you commit something to Ethereum is gonna be there forever and timestamp. But like the Ethereum part here is not is more like for security of the system. It's not that it's a core essential part of the system, which is instead like the circuit that is like the core part of the system. Okay. I I think there's been like a discussion here, but I think I guess you kind of, yeah, sort it out by yourself. Maybe if there's any question, you can just, yeah, open the mic and let me know.
Does anyone have any question? I think there was a question by Zerix panic error, and Ted have already begun to answer. But I think that at the end, how can you you need to put trust in the custodian to not lie about your account, right? Because they might want to lie about it without some user not realizing it if they are not careful enough, right? I think that's what the main point of the RX error. If you want to.
Yes, yeah, that's correct. I mean, like we said it from the very beginning, but I will say it again. Like the yeah, the importance relies on the user performing the verification. There's a new question. Anyone can deploy a verifier for the public, say on testnet, if the circuit is public. Yes, that's correct. Like yeah, you can do it. It's what you get. You will see inside the contracts folder in Summa Solvency. There's a script to deploy the contract, and you can deploy it on a local testnet or on a public testnet or on Ethereum. Yes, you can do that. Okay, so you noticed that I switched to my iPad because I want to go deeper into the proof of inclusion and into the ZK part. So we're not gonna go yet into the code, but this is like the really close to code. So it's gonna be like, let's say a pseudo code session of what's happening inside the circuit. So first of all, we have this. So this is, let's say, the state of the exchange of the custodian at t0. So this is the user base. They took a timestamp of their the user base. They built a Merkelson tree out of it, and they took this thing and they committed to it on chain. So this go to Ethereum. So now we are like at step 3 when user are requesting for their proof of inclusion. So in that case, in this case, we are like considering Henry. So Henry is a user and is requesting this proof of inclusion. So what is?
Excuse me, Enrico. Just Ali has a question. He raised his hand. Ali, if you want to intervene.
Yeah, I'm sorry. You can continue, Enrico. I'll ask it at the end because it's related to something previous. So I'll leave it to the end.
Okay, perfect. So there's like Henry that is requesting their proof of inclusion. So now we're gonna go through, let's say, the process of generating proof of inclusion for Henry. And this is done by the custodian. So first of all, like the simple thing is that we need to, like the input data, we need to start from like the proof of the Merkle proof from Henry. So if this wasn't like a ZK proof of inclusion, you will simply give Henry like this 3 nodes, Henry will compute like the hashing and get to the root and see if the root is matching. And since it's a Merkle-sum tree, we are gonna also perform the summation of the balances while getting from the bottom to the top. So let's declare what are like the goals of our proof. Maybe I should write in black. So we need to prove inclusion of Henry. Of Henry in the tree. We need to prove that the sum was performed correctly. And when I say performed correctly, it's not simply that, 20 plus 10 equals 13, but as we said in the attacks session, we also want to prove that this sum doesn't result in an overflow of the prime, because we're performing this summation in the circuit that works in a prime field group, so we need to avoid this this overflow to happen, because otherwise it will understate the liabilities of the custodian. And other goals are like some succinct verification. I mean, this is general for every zk snarks, but of course we want this verification to be quick. And another goal is like privacy of data. So as we said before, if it was like a Merkle-sum tree inclusion, it will just receive these nodes, and some privacy will be compromised. But since we are like using a zk proof of inclusion, these nodes are like Henry doesn't see these nodes, so there's like some privacy that is saved there. I will just remove this. Okay, so now that the goals are clear, we are gonna go through the how the circuit works. And notice that now we're working with a single currency. So there's just like one cryptocurrency in this Merkle-sum tree, but you will see that in our implementation, we support multiple currencies. So in theory, you can build a Merkle-sum tree that supports all the currencies of your custodian. But honestly, I think we should advise to not do that, because well, it's slower. So I think it's more efficient to do many trees with one or just a few currencies rather than putting all the currency inside a Merkle-sum tree, because the hashing become more complex as you add more currencies. So like the way I kind of visualize a circuit in my mind is, let's say, it's like a box that is taking inputs from one side and performing inside here constraints. So these are like inputs, there are constraints, and there are outputs. So the inputs in the case of Summa, you can think that all the inputs are red, so they are private, while the outputs are public. And just to say, like, if you have familiarity with like Circom, they actually, that's how it works. Like you have like embedded in the DSL the concept of inputs and outputs. In Halo 2 is not that. It's kind of a bit more complex, but if you follow me, you will see that this logic of inputs and outputs still holds also in Halo 2, even if it's not declared or embedded into the API of the system. So our circuit takes 4 inputs. One is the entry. One is path indices. One is sibling leaf node hash preimage. And then there's a sibling middle nodes hash preimage. So this is an array, and this is also an array. I'm gonna explain you what that means. So entry is our Henry entry. So the entry is made by the username and the balance. Path indices is a bit array that is telling what is the relative position of the siblings compared to our node. So if the bit is set to 1, it means that the sibling is on the left of our path, while if the bit is 0, it means that the sibling is on the right. So in that case, we see that our siblings are always on the left. So this will be like 1, 1, 1. Sibling leaf node hash preimage. So is the preimage of the sibling leaf node. So in this case, this will be like greater 20. And the middle nodes hash preimage are the preimages of the middle nodes. So in that will be this thing. So will be 101 left, right, 52 left, right. And when you see in the middle nodes, when you see left and right, basically left is equal to the hash of the left child, while let's do in another column. Like right is the hash of the right child. So now we pass our inputs to the circuit, and we start the computation. So we start declaring the constraints. Okay, I think we have time. We should be able to do that. So first of all, we pass the current balance. So we say like 10 equals the current balance. So 10 is the balance of Henry, and we perform the hashing of Henry and 10 to get the current hash. So you see that current balance and current hash are basically a variable that tells what is the latest balance and hash as we move from bottom to the top of the tree. So eventually, after the whole computation, the current balance will be the balance of the root, and the current hash will be the hash of the root. So this is the first thing, and as we do that, we also output this current hash to the public. So this would be, let's say, the first current hash is actually the leaf hash. So this is going to be released to the public. Then we start like a very big loop. I think I'm going to need more space. We start a loop over each level of the tree. And it's going to be like level 0. So the leaf level will have a different behavior compared to the middle nodes level. So we're going to go through that. First of all, we're going to perform the hashing of the leaf node hash preimage. So hash greater 20, and this will give us the sibling hash. And then we're gonna range check the current balance, so 10, and range check the sibling balance, which is 20. And the range check is basically checking if this balance is inside a specific bytes range. And you will see in our circuit, we have this generic variable called n bytes that defines the magnitude of this range check. Then what we do like a swap constraint between current hash, sibling hash, and the index. So the index is taken from path indices, the first one, and according to what is like the index, this constraint will return as left and right. So it will tell us which of current hash is gonna be, if current hash is gonna be to the left or to the right, according to this index. And another thing that we check here is that the index is actually a Boolean, is a bit, because we cannot put like 2 or 5 in these path indices, and this is also part of the constraints. And after the end of level 0, we set the current hash. Oh, sorry, I forgot the most important thing. And now that we have the swap, we can perform the hashing. So we perform the hashing as hash of next balance. No, sorry, I forgot something else. We also need to perform the sum. So we sum the current balance with the sibling balance to get next balance. So this would be like 10 plus 20. So yeah, current balance is 10, sibling balance is 20, and next balance will be 30. And we perform the hashing for the next level. That will be hash of next balance, left and right. So this is why we need to perform the swap, because if we hash right left, it will be a different hashing. So this would be, we call it like computed hash. And at the end of the level, we kind of update this current balance and current hash. So current balance will be equal to next balance. And current hash will be equal to computed hash. So now we basically, we went from here to, so like at the start of the circuit, the current hash and the current balance was this one. Now we are like here. So we moved one level up inside the tree. So now the rest of the loop will loop over the other levels of the tree. So from level 1 to level 1, 2, 3. And what are we doing in the other levels? It's kind of similar, but it's not actually the same. So we're gonna go through that and then explain what are like the differences. So we're gonna perform the hashing of the sibling hash that for the next level would be 101 left, right, equal to sibling hash. We're gonna range check the sibling balance, which is 101. So now I'm actually, so this is for level 1, but you will apply the same logic also for the other levels, so it won't change. We perform the swap again, same as before. So current hash, sibling hash, and index, and then we'll return like the swapped hashes. We perform the sum, current balance, that now from the previous level was 30, and the sibling balance that is 101, and we get next balance. Then we compute the hash for the next level, so this would be next balance, next balance left and right, computed hash. And at the end of the level, same as before, we update current balance equals to next balance, and current hash equals to next hash. So we do this thing until the last level of the tree, and eventually what we do, the last thing, is just output to the public current hash and current balance. So when we finish the loop, the resulting current hash and current balance will actually be the root hash and the root balance. So this will be released to the public. Oh yes, I wanted to show you like the difference between the two levels. Well, between the leaf level and the middle nodes level. So the first difference is in the hashing. Like this and this are different hashing. Like the one for level 0, let's say the way the input are parsed is different, and also the number of inputs is different. So you will see in the circuit that this is called Poseidon entry chip. Well, I think this is called Poseidon middle chip, something like this. And also another difference is that here we perform like two range checks. So we perform a range check on the entry balance and on the sibling balance. While here we perform the range check only on the sibling balance. And that's just an efficiency measure, because we don't need to perform the range check again on the on 30, which would be like the current balance for this level, because we already kind of in the logic of the circuit, we given the number of levels and the number of bytes, we can check that this this number will not overflow. So this is what I was referring before, and you can check this this logic in the in this generator gen inclusion verifier file. Yeah, so that was the explanation of the circuit. I think we are still in time to take a few questions. I will open the question.
Yeah, thank you very much, Rico. That was excellent. If anyone has a question, please type it in the chat or raise your hand.
Okay, I see that there are already some some question in the chat. So, for example, flying no beta, in the case of overflow, what do you do? Well, so like the
I
overflow.
think it's sorry, Enrico. I think it's part of the challenge that you talked about last time.
Okay.
Maybe.
Okay. Well, I don't know, but okay, I won't answer.
But I think Ali raised you raised your hand. I think.
Yeah, Enrico, my question is actually related to the first part of the talk regarding like public inputs and the checks on the part of the users that they need to make sure of. I was just wondering if the checking of public inputs can be reduced to simply checking that the hash of the block was correct, the hash of the block that was used to do everything. So the hash of the block can assert the validity of the tree, the validity of the verifying contract used, and so on. And it's something that can be checked independently of, say, the Summa website, for example. It's something that can be checked on Etherscan and elsewhere. So is it possible to reduce the this issue of checking the public input to simply checking that the hash block was used the correct one?
Okay, yes, thank you for the question. I go back to the presentation. I think you were referring to this part, right?
Yeah.
Okay, so like like everything, so going to the second part of the question, yes, like everything can be done outside of Summa website. And the funny thing is that we don't have a website. So even if we want to force them to use our website, it doesn't exist. So everything is kind of supposed to work without any dependency on Summa, apart from like the protocol code. And yeah, I mean, I don't really understand what you mean by verifying from the block hash, because like the type of verification that the user needs to do, like this one on the leaf hash, that is like so like this type of verification, I don't see any way to do this automatically, because I mean, they need to enter their username and their balance. And okay, I might have an answer to that. We could potentially do also this verification inside of Etherscan, but what would be the issue there is that in that case, the proof will have as public input both the username and the balance. Well, what we use here is that the leaf hash is the public input of the proof. So if the username and the balances will be public input of the proof, then there's gonna be like some issue, like some risk of privacy leakage when the proof is shared, or even if I'm like verifying this proof through Etherscan, like what's happening under the hood is that Etherscan nodes are like performing this function. So I wouldn't do that, because then you are kind of adding the risk that the proof cannot be shared to the public, because then you're gonna reveal the username and the balance. So I'm pretty sure that I didn't answer your question, but yeah, tell me what is not clear.
No, this is good actually. I was just thinking of like pesky things like, oh, is the right verifier contract being used?
Yeah.
Are we talking about the same tree, the correct tree, things like that?
Oh, yes. Yeah, I mean, like, I think that this will be like I said it before, but I will say it again, that this will be like a great tooling for that might come out from this fellowship independently of Summa, like a simple way for people to verify that a verifier contract that is available on chain is actually matching the expected circuit and the expected trusted setup. So yeah, I think this will be like super useful. I think I want to take this question. So if it's okay for you, I can take 5 minutes to explain this thing about the rain check. Okay.
Yes, please, Enrico.
Okay. So I go back to the free form, which is available also here, thanks to the magic of the cloud. So what is like the point here? Like the question that you are asking is like, why we're not performing the rain check on next balance also in the other levels? Like the answer is that basically we already have a constraint on next balance. Like from level 0, we already know that like next balance is the result of summing two balances, and these balances are already range checked. So we kind of already know what is like the maximum that next balance can get. Okay, so let's go again to the previous example. Like if the range check is that like I don't know, we are range check that value is between 0 and 15. Okay, if we perform this range check on these two values, then we know that next balance can be at max 30, right? So at this point, we don't really need to range check it because we already know what is like the range, the maximum range of next balance. And then at this level, we add a new range checked balance on top of next balance. So again, if we check that this value is from 0 and 15, now we know that next balance can be at maximum 45. And so we can kind of, we already have all the range check in place, and we can forecast what is the expansion rate of the current balance from level 0 to the maximum. So we could do the range check again, but I think it's like overkilling. It's like over constraining something that whenever we can remove a constraint and perform this verification outside of the circuit, I think we should. So again, like we can, since these two balances that are like the input of the summation of the next balance are already range checked, we are basically, yeah, we can forecast what is like the maximum expansion of next balance, even without having to range check it again for each step. Is it clear, guys? Correct. And starting from this, let's say you have like 4 bits and you have like 4 levels, then the maximum will be like 30 plus like 15 plus 15 plus 15 for the number of levels, and we can see if this might overflow the prime of the circuit or not, because the prime of the circuit is known. Okay, I'll take the last question. I think hashing something predictable makes it easier for a well friend to pre-generate signature. So the first check of signing the timestamp, might make it easier to perform hashing. Are you referring to like the proof of address ownership? I didn't understand the question.
Yeah,
hello.
Yeah.
Yeah, so I'm talking about the like slide before this.
So the what? Sorry?
Slide before this. Can you go
Ah.
one slide?
Yes, okay. Like this one or before?
Yeah, the cryptographic proof associated with the like what was it like in detail? To assess the validity of a proof, user should.
Okay, this part, right?
Yeah. The first one, the cryptographic proof associated with a specific timestamp.
Okay, so when I say like the cryptographic proof, it's rather simple. It's like just verifying the validity of the zero knowledge proof. Like when you can generate an invalid zero knowledge proof, so you can generate a proof that based on the KZG commitment is just wrong, for example. So in that case, you will perform the verification of the proof, and this will return false. So yeah, this has nothing to do with signing and stuff. It's just like verifying the zero knowledge proof based on the KZG commitment and the verification key. Why we perform range proof after the level is up? I think what you're referring to is like why we perform the range check on this, like on 101. Because let's think that like when we enter this 101 inside, so this is the first moment when we enter this 101 inside the circuit. So even if like the current balance right now is range checked, we could add a new balance that is coming, let's say, from the outside, is not yet range checked, and this can actually generate an overflow if we add like 254 bits. Like if we add a balance of 254 bits, this will overflow. So that's why we still need to perform the range check on the sibling node balance. Okay, last thing that I want to tell you is like, even if we're not yet going through the code base, I suggest you, if you want to get familiar with the flow that we described today, there's this link that I share in the chat. So this is the flow, like the entire flow that of Summa, and this is like a script that you can run by like this. So you just clone the repo and run the example, and this goes through the whole flow. And also something else that like you will see that if you start looking into the circuit today, you see that there's like a small difference compared like to what I explained today, because while I was preparing the presentation, I realized that we were like over constraining something. So maybe it's kind of, if you want to, there's like this PR that I opened yesterday that is like kind of removing some constraints. And maybe it's also kind of cool to you to see why we were like doing some check that wasn't needed. So this is like a case of over constraining that that's not a problem of over constraining, but it's just less, you're kind of, like worse performance, basically. You can over constrain everything, but it comes at a cost in prover time. Okay.
Thank you very much, Enrico. That was excellent. Thank you. I think we are past the allocated time, and I don't think there is any more question. So yeah, thank you again, Enrico. Thank you all. Hopefully you enjoyed it, and see you in Discord.
See you. Bye bye.
Thank you.